secrets you wish really was part your life. Basic bullies, with no bullets. Does your wifey know you're begging for my notice? Promise you're the same, running for the meds. Show you like my vibe, pass my candy on my wrist. Bad habits, now sit down, you can have it. I see it when you walk my way. Nice big head, come and play with me. Freak it dog, got a whole lot of love for my dog. I see it when you walk my way. Nice big head, come and play with me. Freak it dog, now show how freaky you are.
So I'm just gonna be away for 1 hour. Please don't break anything. And I might have a surprise for you.
Give me a miracle. I need a syllable. Talking about big cash, that's the minimum. I'm done with this trash. Hard to be critical. Show me your mental state before we get physical. Pour some water in your cup, let it drip, drip, drip. Now look straight into my eyes and you sip, sip, sip. It's about time that you shine. Take off that leash so that we can have some fun. I see it when you walk my way. Nice baby, come and play with me. Freak it dog, got a whole lot of love for my dog. I see it when you walk my way. Nice baby, come and play with me. Freak it dog, now show how freaky you are. I see it when you walk my way. Nice baby, come and play with me. Freak it dog, got a whole lot of love for my dog. Freak it dog, got a whole lot of love for my dog. Freak it dog, got a whole lot of love for my dog. Come on, come here, boy. Come on. You freaky dog. I don't need to analyze. Every word that comes out is a lie. Make it look like it's so ice, ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable. Fade eye off the ground, you ain't no one. You a star, blow it up like supernova. In the nighttime, hit my hotline. Sharing secrets you wish really was part your life. Basic bullies, with no bullets. Does your wifey know you're begging for my notice? Promise you're the same, running for the meds. Show you like my vibe, pass my candy on my wrist. Bad habits, now sit down, you can have it. I see it when you walk my way. Nice baby, come and play with me. Freak it dog, got a whole lot of love for my dog. I see it when you walk my way. Nice baby, come and play with me. Freak it dog, now show how freaky you are.
So I'm just gonna be away for 1 hour. Please don't break anything.
Hey, I'm back.
Surprise for you.
Give me a miracle. I need a syllable. Talking about big
Yeah, it's been a bit of a break here from it. DJ Glenlo's been all over the shop.
Show me your mental state before we get physical. Pour some water in your cup, let it drip, drip, drip. Now look straight into my eyes.
So enough of the apologies. Yeah, there's been a big expo in Melbourne, and I was there interviewing lots and lots and lots of the exhibitors. I think I got through 19 of them. And then I had to edit all the videos, and boy, there's a lot of work. So I was kind of holed up in the editing suite for a couple of weeks, but there we go. It's all done now, all done and dusted. So as you probably saw if you got the DM today, today's all about the much anticipated change to New Zealand standards particularly for solar and battery systems. I think there's 300 or 400 standards that all got refreshed on the 13th of November, but I'm going to be talking about only a few of them, the ones that relate to the solar and battery industry. So that's kind of my plan for today. But as always, I just love to hear from people where you're watching this from. Give us a shout out in the chat if you can, and I'll respond to any questions live if you've got them. So that's always a good thing. So just in the chat window down there, how you going? I'm going to type. There we go. So. Other announcements. Well, it's raining, so if you hear some background noise, we're just a big rain event just hit us, and it's a tin roof above me. With even though it's got sound insulation, it still makes its way through into the studio a little bit. It's amazing what sound recording equipment can do these days, and also editing equipment. I find that using AI, I hate to mention that word, it can actually remove all that noise in the post. But there you go. Oh, g'day, Glenn. Glenn FBWA Stories. Wow, another Glenn. My namesake. Even spell it like me. That's kind of cool. So, yeah, we're going to be talking about New Zealand standards. So let me give you a bit of a backstory. Not everyone's aware, not everyone's actually particularly involved in New Zealand standards unless you're working in New Zealand, but Australia and New Zealand share common standards, both electrical, gas, engineering, all sorts of things. But in terms of the electrical space, the ones that I'm most involved in, and I'm on the committee that helps write those standards, EL42 for inverters and solar installations, and EL005 for battery systems. And we've been updating those standards progressively over the last 20 years. It's been a long time. But one of the problems has been that the process in Australia is that once a standard is published, there is an adoption period that's often written into the standard, but some state regulators will overrule that, have their own requirement. But it's generally something like 6 months or something. But New Zealand requires a change to the government regulations. So the New Zealand electricity regulations have to actually be changed, and it affects a lot of standards, not just the solar and battery ones. And that's been sitting there since 2010, unchanged. So I like to say that New Zealand's been in the Bronze Age, really, when it comes to standards compared to what's currently available. There is some acceptance of some of the clauses from the newer ones with a bit of wiggle room. So the 2014 edition of 5033, for instance, is sometimes used to allow things like microinverters and other MLP devices, optimizers, etc. And I call that the Silver Age. But we're now, in terms of 5033, up to 2021 edition. And for 4777 Part 1, the installation standard for inverters, we're up to 2024, so it's the new age. Yeah. So at last, we've got both on the same standard, the same date, which is fantastic. Now, I'm going to give you a bit of a highlights reel of some of the changes, but I'm also going to be running a course, so a little bit of a plug for that. I'm going to be running an online course. It's going to be interactive, so it's run via Zoom, so you can actually talk to me and interact with me. And that course will be on the 10th and 11th December. And it will be New Zealand time, 11 a.m. till 3 p.m. So it's 4 hours each day, 2 days. So it's quite a big course. I just put a link in the chat there to it. So if you find this interesting and you think it's useful for you, you might want to enroll in the course. So it'd be effectively 8 hours of training. And it is all recorded, so I share the recordings with those who attend afterwards, because often people have to drop out, they've got work commitments or they can't make both days. So there you go. That's my little plug for my course coming up. But anyway, this is a sort of preview of some of that content, and just thought I'd get a bit excited about the fact that at last New Zealand and Australia are in lockstep with our solar standards. So g'day, Andy, from sunny Melbourne. It's the rain must be going your way, because it's been raining here for about an hour. And so good to have you both on board. So what else? Bit of news too, and I suppose this is kind of a little bit of an explainer really, but you probably realise I test a lot of products here at the Smart Energy Lab, and I get very excited by the good ones. And one of those good ones has been SIG Energy. I liked it so much I put one on my house, along with about 30% of all the other new installations in Australia. So it's amazing how that product has taken off. But they had a bit of a bump recently where there's been some issues with particularly the single phase, the big single phase, like the 10 kilowatt units, overheating on their AC connection. Now, from talking to SIG Energy and seeing some of the examples, it does look like it's installer error. You are provided with ferrules to crimp using a ferrule crimper over the multi-strand wires, and it does look a bit like there's been issues with compliance with that manufacturer's requirements. But let's leave that open because we don't really know yet. There's probably going to be more investigation. But the good thing is that SIG Energy have announced they will happily replace any damaged units. So they've kind of done the right thing. If there is a problem, they'll fix it. They'll pay installers to go back and fix it. But if there's not, if it's an installer error, well, something you should negotiate on. But an engineer actually raised an interesting point. And it's to do with the change in our inverter test standard 4777 Part 2, which even though it is a relatively new standard, it still is being applied in New Zealand because it's a test standard for inverters. It's not an installation standard. It doesn't have to be referenced to New Zealand electricity regs. It's really up to the DNSPs, or as they're called in New Zealand, the lines companies, to determine what they require when you connect an inverter to the network. And in New Zealand, that'll be 4777 Part 2, the latest version, 2020. Now, what's changed from the previous versions is the low voltage ride-through was introduced to the 2020 version. Now, an engineer pointed out to me that this may actually exacerbate problems with poor connections. So his explanation was, and I'm just looking at his email right now, that in the old days, before low voltage ride-through was required, a loose connection at the inverter output would be detected, leading to the inverter to shut down. A loose connection creates a high resistance, localized heat, and eventually carbon built up. This results in a local voltage drop within the premises wiring right at the point of connection. This will be detected as a loss of grid fault and cause that loose AC connector to be basically disabled to prevent meltdown because of that local voltage drop. But with the change in 4777 Part 2 to require low voltage ride-through, we've now got this requirement that the inverter keeps trying even when there is a drop in voltage. So now the inverter will go, it'll fight the problem. The inverter's firmware detects the voltage drop at the terminals caused by a loose connection or high resistance, and its primary response within its operating limits is to try and maintain the required voltage and push more current, especially during periods of high solar generation. So ironically, that fault will be exacerbated by the low voltage ride-through requirement, and that excessive heat could lead to melting of connectors. And also, it could delay any potential shutdown as a result. So, yeah, I tend to agree. This is a senior engineer from a Melbourne company that I know, and I trust his opinion. So that's really interesting. We may actually have a case where an update to the test standard has made inverters a bit more problematic when there is a fault. That's a bit unfortunate. Anyway, let's talk 5033, 4777, and 5139. Now, what I might do is just bring up on screen here. This is from the publication of the Electricity Safety Standards, the amended regulations 2025 that were effectively came into force with a 1-year adoption period on the 13th of November this year in New Zealand. I just took a screenshot of some of the standards there. As you can see, 4509 Part 1 is still the good old version, 2009. Actually, it never even changed. The irony is we're just about to publish a new version of 4509 Part 1 and 2. And I know there's going to be some people out there who really like to be able to use the new version of Part 1. It's got some really user-friendly features in there now, which have been called out for a long time. Things like being able to have a socket inlet for generators. So yeah, you missed out, New Zealand, on getting 4509 Part 1 updated, but the good news is that 5033 and 4777 Part 1 got picked. Now, what's missing in that list, though, and this is really curious, and I'm still waiting to hear from Energy Safety New Zealand what their view will be, but the battery standard, ASNZS 5139, the 2019 edition, wasn't listed. Now, the explanation given to me was that this is a update of existing regulations, existing standards, and since 5139 wasn't an existing standard, it would have to be added as a new standard. So another amendment. I'm not sure if and when that might be happening, but there is a curious kind of correlation, and this is why I'm going to be talking a bit about 5139 today. Previously, WorkSafe had said to me that even though 5139 wasn't referenced to New Zealand electricity regulations, it was best practice guide and it wasn't replacing an existing standard. So ultimately, it could be used in a court of law. So that's kind of a soft enforcement. If things really go bad, if the brown stuff hits the fan, you could be charged with not complying with the recommended best practice for safety. But now here's the interesting conundrum, is that ASNZS 3000, the 2018 edition, is now referenced in New Zealand electricity regs. Now that's a big hurrah for all electricians in New Zealand, because there's a lot of improvements in that standard. But if you read the list of normative standards at the beginning of 3000, the 2018 edition, it lists ASNZS 5139 as a normative standard. Now, how does that work? If you're not familiar with the terminology, normative and informative, a normative standard is one that, in order to comply with the parent standard, in this case 3000, within the scope of the normative standard, you need to also comply with that standard. So, in effect, and this is kind of my opinion, but let's see what WorkSafe New Zealand say, that if ASNZS 3000 2018 edition is now the current version in New Zealand, you still need to comply with ASNZS 5139, the battery standard, even though it's not listed in the electricity safety regulations, because it is a normative standard. So there you go. Take that for what you will. But I should probably emphasise that 5139 actually is a pretty important standard for safety of battery systems, particularly lithium-ion batteries. And so you really should get to grips with it if you're installing lithium-ion batteries. Okay, remember, if you have any questions as we chuff along, please feel free to ask me. And I'm just looking for where my next slide's going to be. And where's it gone now? Here we go. Camera number 3. Okay, I've got a lot of screens going on here. Great, there we go. So I'll start with 5033, the PV array standard. Now, I actually produced this little presentation back in 2024, but it's still the same one. And I'm not going to go right through it. It actually really is a substantial part of a course, this one, but just to give you some of the highlights in terms of what's new in the 2021 edition. So now there's a little bit of an introduction of me I forgot at the beginning of this. That's where I live, by the way, for those who don't know me. I live about 65 kilometres from the Melbourne CBD in the Yarra Valley, on top of a mountain, 700 metres above sea level, Mount Tulibuang. And it's where I have my smart energy lab, where I have a lot of products that I test and get to know. And it's also where my home is. I live on an off-grid community. It's 51 years old yesterday. We just had our birthday party, our 51-year birthday party for the community. There's about 70 people who live here. And you're looking at just one of the 6 clusters there in this picture. So it's on quite a large property, I think 245 hectares, basically a mountaintop. And it does get pretty cold. We get a bit of snow in winter, and it's never too hot in summer, which I like. So let's look at the preface of 5033. These often give you some little highlights about what's changed. And there are a number of changes. As you can see, I've highlighted two really important ones. And the addition of DC conditioning units for voltage and current calculations. Now, you might say, well, what are DC conditioning units? So anything that modifies voltage, frequency, or current is considered a DC conditioning unit. And that means it can be used to optimize the performance of any panel. Now, I'm just going to switch back to me for a second. So you might have a range of panels. Some are in shade because there's a tree, and some are in full sun. In a normal string system, you will get some throttling of the whole array when there's a mismatch of production of current within the array because the panels are connected in series. But with devices known as MLPEs, module level power electronics, such as microinverters and DC conditioning units, they optimize every panel individually and then contribute as much as they can to the string. Now, they haven't been referenced in the earlier versions of 5033 that were previously in New Zealand's regs. The really old 5033, the 2012 edition, it wasn't referenced. So technically you couldn't use them. Or if you did, you had to put a DC disconnect on the input of every single one of them, which would be just a nightmare. So that's good news. But it now introduces a kind of a new problem, which is you need to be able to calculate what the currents will be on the array, because you've got something that is modifying the output voltage and current of a module and contributing a different output voltage and current to the string. And therefore, as far as things like cable protection and cable sizing, you need to understand what that transfer is. So there's some calculations for that in 5033. We've also made some changes to the requirements for isolation of those DC conditioning units. Basically made it much simpler. Just the fact that the plug and socket itself is deemed to be on the PV module side of the connection. Perfectly okay to disconnect even when it's operating because it's below extra low voltage levels. So there you go. Those are a couple of two key ones. We've also got some more signs. Yay! No, not yay. I don't know why I said that. Signage is just one of those things that just keeps on giving. So where am I? Trying to find my slides again. Yeah, so I think I've said this probably about 50,000 times, but countries like Germany, they have only one sign on an installation for a residence that has solar, and it's basically a picture of a house with a solar panel and the sun. And the German approach is, you should know what you're doing. So they trust their profession. Somehow we kind of try to treat our electricians as that they don't understand anything, and we have to put up signs everywhere. But anyway, it is what it is. Some of that signage is relevant to non-electrical workers, things like the circular green sign with letters PV on it to warn that there is a PV system installed for first responders, so they know there's solar panels on the roof there. And some of them are for the end user, things like a shutdown procedure, just so you don't have to go and look for the manual. It's sitting on the wall there telling you how to turn the system off. So what else? So the scope has changed. Now, this is actually a big deal. This is a big change. So it says this document does not apply to PV arrays. So it's stated in the negative, does not apply to PV arrays in the following electrical installations: less than 100 watts and less than 35 volts at standard test conditions, open circuit. Now, basically, every residential panel would be, well, some might be just on 35, most are more than that anyway. So if you even got one panel on your roof these days, you're in scope. So it picks up a lot. What's not in scope is transportable structures and vehicles, because they have their own standard 3001, and there's also a standard for boats, 3004. And if you're in the RV or caravan industry, you should check out 3001, because it's changed, and I haven't checked this, but I imagine it's also been updated in New Zealand regs. It's got a lot stricter about where you can put a battery in a caravan. So, for instance, you can't put a battery in a habitable space anymore, even in a caravan. So it's got to be more or less treated like a gas bottle. It's accessible externally, but not internally, and that's really about explosive gases and toxic fumes under fault. So yeah, that's a big change. Also, understanding what hazard levels are. So I drew this little diagram to sort of explain why the hazard level can vary in terms of risk of electric shock. We're moving away from the old terminology of low voltage and extra low voltage. So to define those in 3000, extra low voltage is less than 50 volts AC and less than 120 volts DC. But in the IEC standard, 62109.1, which is for inverter systems, it states a matrix of risk depending on voltage level, voltage type, and environment. And voltage level would be volts, voltage type AC or DC, and environment wet, dry, or damp. So anything over 35 volts DC in a wet environment is considered hazardous, and that's why 5033 now considers anything over 35 volts needs to have a certain level of protection, restricted access to all of its wiring, and all of its wiring up to its disconnection point. So that's a big change. But for a dry environment, such as where you put a battery, like you might think I put a battery outside, but the battery itself is in a weatherproof IP65 or better enclosure. It is actually dry in the side, so it's over 60 volts is considered hazardous. Anything over 120 volts is now considered, this actually depends on whether it's a wet or dry environment, anything over 60 volts in a dry environment is considered the same as LV. So 60 volts becomes a pretty important demarcation point. We'll talk about that more when we get onto batteries. Wow, I'm just looking at the time. I just realized we're going to probably have to run this over several sessions because there's a lot to talk about. But like I said, I wanted to just get your heads around some of the changes. So what else? So restricted access is being better defined in 5033 2021 and lists 4 ways to restrict access. Remember, you need to have restricted access to all of the modules and associated wiring if it's over 35 volts. So that means a ground mount system, for instance, would need restricted access. Now, the old kind of restricted access tended to be like a cage people would put around something, but no, it's actually simple in some regards. So it now can be as simple as just a barrier, like a fence. It can be by location, so i.e. on a roof, as long as it's over 2.5 meters to the wiring system or the modules. It can be by an enclosure. Well, you could put a cage around something like an inverter, and or you might just enclose the parts that are the PV array. So there are many inverters that have the ability to bring conduit straight into the inverter. So you've actually provided restricted access by enclosure. It doesn't have to be a cage around the whole product. We've also got some new terminologies in the glossary. So things like IBF total, that means current backfeed total of a PV array. We've got IC break and IC make, which is for the instantaneous rating for DC isolators, and that's a good one because it means we understand that some DC isolators, even though they might have a relatively modest continuous rating, have a high instantaneous rating. And also current for DCUs, their overcurrent protection rating. There's some new notation coming along. So this standard applies to not just PV arrays connected to an inverter, but PV arrays connected to an application circuit. There could be a maximum power point tracking charge controller, a pulse width modulated charge controller, It could be directly to a load, or it could be to an inverter. And the inverter might be what's known as separated or non-separated. Those terms are really, in common parlance, is transformer-based, i.e. the DC is galvanically separated from the AC output, or non-separated, which is the DC is not galvanically separated from the AC output, which is the norm for basically all inverters these days. And we don't use the word inverter in the standard, we use the word PCE, power conditioning or power conversion equipment. Can't remember which one it is. Power conversion equipment, there it is. It was on the slide. I should have seen that. So just note PCE. There's another terminology used internationally a lot too, PCS, power conversion system, but we don't use that in the standard. So just be aware. We also try to identify some of the areas of misunderstanding when it comes to calculating the current ratings on a product on PCE. So you might think you've got 3 inputs on an inverter, but some inverters will common those inputs internally, and therefore you've got 1 MPPT with 3 plug and socket connections for 3 strings of cables. Or you might have, as in the top example, 3 separate MPPTs. Now, when it comes to calculating maximum voltage and maximum currents, you base it on per MPPT. You don't sum them all together. So if you've got 1 string at 600 volts, 1 string at 500 volts, and 1 string at 400 volts, the maximum VOC is just the highest of one of them, which is 600. But when it comes to current, we no longer require a signage saying the fault current of the array. We just need to know on the site map, and that's another new requirement, is actually to have a site map, what the kilowatt peak rating of the arrays is, total array. When you've got parallel strings, now you will have a sum of currents. And so you do need to calculate the maximum current based on the sum of all. So there you go, slight change there. I'm just looking to see if there's any questions. No? All quiet, all good? Yep. So just to come back to DC conditioning units, I've got a little picture explaining sort of how they work. So there's one actual DC conditioning unit just sitting there. And they're quite small, they're sort of, slightly bigger than a pack of cigarettes generally, and they clip onto the back of the module. They've got 4 leads, 2 in and 2 out. The 2 in are from the module, and the 2 out connect in series into the string. And they live generally underneath the module out of the sun and provide you with that individual panel level maximum power point tracking. Some DCUs also provide other features like some module level monitoring, something called rapid shutdown, which is where when you turn off the PCE, every single DCU turns off as well, and therefore there's no dangerous voltages coming off the roof. The highest voltage is just one panel. So that's quite a nice safety feature. When it comes to faults within a PV array, we need to be able to calculate the prospective fault currents, and at which point we are required to introduce string overcurrent protection. Now, this isn't that new. We've only just adjusted some of the values a little bit, but it still is one that can trip people up. There is no simple rule like 1 string of panels, no string overcurrent protection required. That's true. 2 parallel strings, if you have a fault in one of them, still no string overcurrent protection required, because if you've got 1 good string and 1 faulty string, the highest current still is just 1 string. So that's fine. But once you have more than 2, you need to do a calculation to find out whether the sum of the parallel fault currents, that's generally referred to as n minus 1 the number of strings, because you have a fault in 1 string, so there's n minus 1 number of strings still producing current. And if that sum is greater than the fuse rating of the module, then it can thermally damage the faulty string by reverse currenting that string. So don't assume that when you get to 3 you will need it, but it's quite common. It just depends on the ratio of the ISC of the module and the fuse rating. Okay, I'm just going to skip over a few slides here. Where's my, oops, I clicked on the wrong thing. And just still no questions come in. I guess you're just listening there. Why has my slide stopped playing? Seem to have a little problem here. Oh, okay, got it working again. Oh, that was strange. All right, so I'm trying to find a simple diagram to show you. Here we go. Not so simple, but anyway. Evil laugh. So when calculating protection from overcurrent for a PV array, we used to just think of the current coming from the PV array and to ensure that the cables were correctly sized. But now we consider 2 other possible sources of current into the array. One of them is backfeed from the PCE itself, whether the inverter or charge controller can provide reverse power from another source, and whether there is any external DC coupled storage or source on the array as well. Now, that little yellow box there called external source is a pretty rare phenomena, but there were a few products that actually had storage on the PV array string. So there's even commercial products that do this. I know Amped from America, they do this at a utility scale. They call it reverse DC coupling. I love that term. But you've now got other potential sources of current into an array. And so you need to calculate on all sources. When it comes to backfeed, backfeed is something you'll need to check with the manufacturer, but pretty much your standard inverters don't provide any backfeed. Where it most likely occurs is with non-galvanically isolated charge controllers. They often have a common positive or common negative going to a battery, and depending on which leg of the array the fault's on, you could actually have full battery current limited only by the battery over current protection device flowing back into the array. So that's where it gets pretty important to calculate all of those potential sources. All right. Here's a curly one. Maximum string current. So we've actually got 3 scenarios here for calculating maximum string current. What we used to have was basically the the short circuit rating of the module, ISC mod, times 1.25. That used to be the way to calculate the maximum string current. And the reason for that 1.25 times multiplier, which incidentally has been in all of the standards, even back in 2012, we had the 1.25 times multiplier. And that was to accommodate 3 things. It was to accommodate a radiance greater than 1,000 watts per square meter, because current from a module is proportional to a radiance, and modules are tested at 1,000 watts per square meter. And New Zealand will often get, on a clear, sunny day, more than 1,000 watts, more than 1,100 watts, maybe 1,150, even 1,200. It's amazing. So that means another 10, 15% current. So your module short circuit current rating will actually be much higher under higher irradiance. And the other thing is to consider you will get module mismatch. So you might think you've got a module that's a 470 watt module, but it'll say 0 to plus 3%. So you might actually have a plus 3% module In the old days, they used to be up to +5. It's pretty amazing, or plus or minus 10 even. So if you've just got a bit of a lucky draw and got all the good modules, you're going to have a higher current rating just on their positive tolerance. And the third thing is a bit of derating as well. So you'll get derating of things like protection devices due to temperature. So that 1.25 times multiplier has always been there to kind of safeguard against those eventualities. But now we've added the K factor. Yeah, the K factor. So this is for bifaciality. Bifaciality is what K stands for. Now, if you've got a module that's got basically a white back sheet on it, its bifaciality is 1. That means has no impact. But if you've got a bifacial module, you need to calculate the bifaciality, and that will depend somewhat on how it's installed, whether it's exposed to reflected light from a roof or from the ground. So some manufacturers actually put a bifaciality factor for different conditions on their data sheets, but there is in the appendix for 5033 a methodology for how to calculate that bifaciality, and therefore it will impact on the maximum current as well. I mean, I'm just a little aside here. I'm just about to go to China to talk at a conference for a company called Tongwei about their new TNC 2.0 modules, and they have 88% bifaciality. That means the back of the panel can produce 88% as much power as the front. Whoa! Mind you, you would need a lot of albedo to get that full 88%. Maybe just something like a white roof or snow, but it's certainly going to give you a big whack even off grass and if you've got a tilt frame or a tracking system. So yeah, bifaciality is a thing now. So if you've got no DCUs, you just got a conventional string of panels, then you use that formula at the top. But where it gets complicated is when you have some DCUs. Now, what am I talking about there? Well, it is possible to partially deploy these DC conditioning units depending on the product. So if you're using SolarEdge, for instance, it's all or nothing. SolarEdge don't actually have an MPPT in their inverter. They rely on the optimizers to do the MPPTing, if that's ever a word. But some brands actually are designed to be partially deployed. So Tego is quite a well-known brand. So you can deploy individual Tegos on what people often call the problem panels. You might have a panel that's got a bit of shading, it's near a gable or a chimney, and it's always going to get a bit of shading, so you might put some Tegos on it. Huawei also have partial deployment as a variation as well, so you can do full or partial deployment with Huawei. Now, there are other brands as well, but if you are doing partial deployment of DCUs, you've actually got to use this part of the formula, which says that you've got a choice of either using the maximum output of the DCU, so IDCU string max, and that can be pretty damned high. I mean, I think I looked at a Tego, it's like, was it 80 amps? Like, whoa. Though you're unlikely to achieve that, but that's what it says. Or you use the formula from above, the 1.25 times K times ISC mod, whichever is the greater. Now, generally, it will be the first one. It will be the IDCU string max of the product, so you tend to have to use that. But if you've got a full deployment of DCUs, all modules have them on, you can actually use the the DCU string max as your maximum output. So you don't have to use any other formula. So just beware, this can trip up your selection of cable if you're not aware that your DCU actually has a very high potential current output. Even though you probably won't see it, it is a potential. So there you go. Okay, I'm just skipping through here. Right, okay, earth faults. Earth faults are a bit of a nuisance. They're a real nuisance to try and find on the PV array. Lots of reasons. It could be a damaged panel, like hail, but it could be a faulty manufacture, and that's one of the toughest ones to find. So water has got in somewhere, and it's bridging to the frame. and it's causing the earth fault alarm to be triggered. But as soon as you sort of get out there, it's a sunny day and it's dried out and you can't detect the faults anymore. But it's a requirement to be able to protect against earth faults and calculate the maximum voltage if it's above 35 volts. And you will be required, if it's over 120 volts, you will be required to provide both fault detection and an alarm function. Now, that's pretty standard on inverters these days, but where it's not so common is on MPPTs. There's quite a lot of MPPTs that don't have this functionality, and technically you need to add it as an additional feature. So there are add-on products. They're quite expensive. They often cost more than the MPPT. So when considering a DC coupled system that's using an MPPT to charge a battery, for instance, choose one that has earth fault detection and alarm functions. To name some brands, things like AERL here in Australia manufacture all of their MPPTs with earth fault detection and alarm functions. Schneider with their 600 volt 80 amp MPPT. Victron with their RS 450, and I think they will be bringing out some more high voltage MPPTs which have earth fault detection. So yeah, they are available to you, but yeah, just be aware that it is now a requirement once you get over 120 volts on the PV array. And incidentally, that's the open circuit voltage. So you do need to calculate the voltage temperature compensated. And if you want to do it the hard way, but the good way, there is formulas for doing it. I've just shown a little bit of theory there on how it works. You've got to know what the coldest operating temperature is going to be, and then you can calculate how many degrees below test conditions that is, and you multiply that by the coefficient for open circuit voltage, and it'll give you a percentage rise. So if you're in the South Island on a sunny winter's day, you could be getting, considerably, maybe 10% more voltage. So it does matter when calculating maximum voltage. And we only ever consider the maximum voltage temperature compensated in the standard. So wherever it says maximum voltage, always refers to temperature compensated maximum voltage, never standard test conditions. Cool. We're up to now. Oh yeah, so just hanging in there with the calculating maximum voltage. There's a couple of ways of doing this, by the way. You can do it using 4 methods. The first method was the one I just showed you. You actually calculate it from the data sheet, and it is the recommended one. The standard does say, it says to do it that way. If not possible, it gives you 3 other methods, and they are according to the manufacturer's instructions. So I've never seen it, but if the manufacturer actually gives you voltage open circuit at different temperatures, you can use those. But the most common method and used widely by inspectors is just look up table 4.1. Now, a word of warning here, table 4.1 hasn't changed since the very first version of 5033 was published. And it's using a percentage rise due to cold temperature that is way out of date. Something like 0.5% per degree, negative 0.5% per degree is kind of what it's using. These days, modules are 0.3, 0.25, so even half that now. But so table 4.1 actually puts you at a disadvantage. So you're much better off doing the actual calculations. It often means you can get another panel in a string and stay under your maximum voltage limits. Speaking of which, and I probably should have headlined with this one, 1,000 volts, guys. 1,000 volts for residential. Yeah, 1,000 volts. Do I hear it for 1,000 volts? Okay. Whoa. Yeah. That's one that's been a long time waiting. Even in Australia here, we kind of thought we had it, and then we didn't because we had to update the inverter standard as well. but now they're both in lockstep. So 1,000 volts for residential is okay, up to 1,000, sorry, and up to 1,500 volts for non-residential. So there you go. That's a really big change. And it's particularly if you're doing, three-phase systems. Most three-phase inverters don't really hit their stride till they get up over 600 volts. So that's a really good thing. So table 4.1, most commonly used, but I'm just saying you're disadvantaged using it if you're trying to get the maximum number of panels in a string and stay under 1,000 volts. Though that's a lot of panels these days. And number 4, I call you live in Antarctica because if it's below minus 40 degrees, it's not linear generally. So you need to actually find out what the maximum voltage is at sub minus 40 temperatures. So I don't think that's going to be common in New Zealand, except down at Ross Base. So there you go. No questions yet. You're a quiet bunch. I love it when people tell me where they're watching it from. I've got someone from sunny Melbourne, and it's no longer sunny, and that's Andy. And I've got Glenn from Sydney. I wonder where else you guys are coming from. Just throw something in the chat. Let me know. It's always good. Okay. Segregation. Now, segregation is been in 3000 forever, but it's talked about segregation of basically communication systems from LV cables. But they've only really considered LV AC cables. It didn't really consider LV DC cables. So we now require effectively 3 levels of segregation in a PV array or PV system. You've got to segregate your LV AC from your LV DC from your comms or anything under extra low voltage. So you might have some, some control circuits. So that segregation can be achieved by various means. It can be achieved by distance of 50 millimeters. So if you're using tray, for instance, you can secure cables at extremities of the tray. If it's a wide enough tray, if you're using 300 mil tray or even 150, you might be able to clip your cables into position so that they're 50 mils apart for LVDC, LVAC, and comms. You can do it by enclosure. So you could put, for instance, your comms and conduit and just lay them in the tray and still have your 50 mil separation from your LVAC and your LVDC. Or you can do it by insulating partition, or earthed partition. So there's quite a lot of ways to do this. And once you enter an enclosure, it gets more problematic. So if you're trying to bring AC, LVAC and LVDC into the same enclosure, then you need to have IP4X segregation. So that's a 1 millimeter probe separation and no common conductive parts between the LVAC and LVDC side. So no common DIN rail, for instance. You might say, oh, hang on, but every inverter's got LV, AC, and DC floating around inside it, and they don't necessarily have that level of segregation. That's because an inverter is tested to a standard, and that standard requires certain levels of creepage and clearances for a manufactured product. But when you're sort of DIY manufacturing an enclosure, basically building something, you're not getting it tested, so you have to comply with this spacing. G'day, Scotty from Pakenham. And Thomas, g'day, Thomas. Thomas says, Glad you mentioned you don't use the STC for calculating maximum voltage. Absolutely correct, Thomas. The STC has got no relevance at all in the standard for safety. It's just an indication of what happens at 1,000 watts per square metre at 25 degrees cell temperature. It's a test condition. It's not a real-world condition. So you always have to use temperature compensation. So, yep, thank you, Void Ranger. He threw the equation in. Very good. Yeah, nice bit of mathematics there. Yep, perfect. And I note that you're using a temperature coefficient which is more modern, the 0.0025, whereas these days, if you're using table 4.1, it'll be twice that. So, yeah, don't use table 4.1 if you've got access to the data sheet, because then you can just do the proper calculation. Cool. Where are we up to? Okay. That was a good question. Thanks, Thomas. Labels. I knew I had to get onto labels eventually. Now, this is probably a case where New Zealand rocks and Australia took a long time to catch on. Australia required the dreaded rooftop isolator up until 2021 edition of 5033 was published. I was actually the lead on that subcommittee on EL42 to try and find a solution to this problem. And I remember on day one of our meeting, I said, hey guys, this is going to be easy. We just need to adopt what's already in the standard for New Zealand, which is you don't need a bloody rooftop isolator. You can just basically have a disconnection point on the roof, the plug and socket, and put a little sign on there saying do not disconnect under load, and sweet, no problem. Well, we met twice a week, once a fortnight, get that right, Glenn, for about 9 months before they agreed. Somehow people hang on to these things. They really like the idea of a switch on the roof that burns, but there you go. So there's a bit of a change though, which is we now need a warning sign. So we need a sign, that indicates where that disconnection point is on the roof. So it needs to be within 150 mils of the plug and sockets, and you need to have the most positive and the most negative part of the string in the same location. What does that mean? Well, if you're doing a row of 10 panels, you've got to have a home run cable that comes all the way back to the beginning again, so that you've got your most positive and most negative as your disconnection points right adjacent to each other. Typically they will be underneath the module, but they need to be within 150 mils of the edge of the module, that's so it can be reached. They need to have a label across each of them indicating not to disconnect under load. That's always been the case in New Zealand. And you need a sign on the side of the module saying disconnection point so people can find it. So there you go. That's the requirement. But if you really like the idea of a switch on the roof, you can still do it. It's not verboten, but it seems like a really bad idea. You can have a load break disconnection switch. Cool. Now, there is actually a condition where you kind of do need a load break disconnection switch after all, and I better run that one past you. It's probably becoming less common, and it's sort of highlighted in this flow chart here, is that starts off, do you need an additional load break disconnection device? Are there more than 2 parallel strings? So if you've got more than 2 parallel strings on the roof or at the array, and you say yes, okay, I've got 3. Is there string fusing on all parallel strings? And if I go no, then I need an additional load break disconnection device. Oh, bugger. If I go yes, are the strings paralleled at the load break disconnection at the inverter? So do you bring the strings down to the inverter and they parallel at that point, not on the roof? If it's yes, we don't need those load break disconnectors up on the roof. We've got one down at the inverter. But if it's not, if they're paralleled on the roof, we do need a load break disconnector. So I guess the not exactly the rule, but the recommendation there is just avoid having more than 2 parallel strings connected on the roof. And you can just get away with having the plug and socket as the point of disconnection. And Scotty says, also a sign indicating what string number it is. Oh, thanks, Scotty. I didn't know that one. I don't know if you know what clause number that is, but yeah, would make some sense. Okay, so just running through those scenarios for disconnection, I drew this little summary slide here. And as you can see, we've got 2 parallel strings, so no load break disconnector required. We need to have that little warning sign and indicate that this is the disconnection point, and that can be the plug and sockets on the modules. or the combining point. If we happen to go to 3 strings, now we introduce a load break disconnector, and we had to have a sign saying PV array DC isolator. And then we can do that as 2 separate isolators ganged, one with 2 parallel strings, one with 1 string, or we can have all 3 ganged parallel together if you do have a suitably rated DC isolator. The currents can be a bit of a problem if you have a fairly high current for load break DC isolators. And if it's a microinverter system, remember there's no DC at all, needs to be disconnected under load. You just have an AC isolator adjacent to the array. Now on the right-hand side of that picture, I'm showing the PV sign, but in tiny lettering, it's probably too small for you to see, is the letters indicating the nature of the disconnection. So when it's a disconnection point, you put the letters DP. When it's a switch, you put the letters SW. And when it's a microinverter system, you put the letters AC. So that's the information to first responders about how they disconnect the device. I see Scotty, all right. No, just our inspector defected us and we didn't identify which string the DP is on. Okay, Scotty, I always like to know what clause they apply when you kind of get pinged on something, so it's probably worth asking politely. Just to be aware that inspectors can be fallible. Sometimes they have their own rules and they're not in the standards. But I don't want to be too assumptive here, so we'll see. Oh my gosh, time is flying. So I definitely won't be getting onto 4777 Part 1 and 5139 today, but I think that's a topic for next week. So let's talk about restricted access again, because that is kind of a bit of a new one, bringing it down to 35 volts. So wiring enclosures for wiring systems. Now, wiring enclosure can be conduit, it can be, a cage, it can be lots of things. A way of protecting for the means of restricting access to the actual conductors or the potential parts of the system that carry hazardous voltages. So in the case of having a disconnection point, restricted access only applies up to the disconnection point. So that means, let's talk about a standard residential installation. The panels are on a roof and the roof is over 2.5 meters. So it's restricted by location, by height, and the disconnection point is on the roof. So that means you don't have to have anything special in terms of restricting access at the inverter, because it's quite common to have the conduit coming off the roof and then up to 300 mils of exposed cable at the inverter plugging into the plug and socket on the PV inputs. Those PV input points and cables don't need restricted access. When it's HD conduit, it's required if it's inside a building, and medium duty if it's outside a building, though in New Zealand, HD conduit seems to be the norm for all conduits, so there's not a problem. And when you're less than, you don't need to protect the cables. Hang on, let me just state this a bit differently. I think I need to jump out of this slide and show you something else. I just realised it's going to get a little bit complicated. There we go. All right. This is a big one too. We have on the Standards Committee a range of stakeholders, including fire services. And fire services are the people who often have to go into a building during or post-fire, and there may be a PV array on the roof. Their concern was that in a post-fire situation, they often will, or even when it's not too dangerous, they'll try and pull down the internal ceiling to provide access to, put out fire inside the ceiling space. What they want to know is they're not pulling down live wires, because they know that the PV array is energized from the sun, not from the grid. So they wanted us to ensure that within 1.5 meters of an external wall of a building, there are no cables lying on the suspended ceiling. They have to be 600 mils above the ceiling. They did have the allowance, though, that within the zone of 1.5 to 1 meters, 1 meter, you could drop down at that point in the highest possible level, so on the underside of the rafters. And once you get within 1 meter of an outside wall, you can actually drop down onto the ceiling. So that's why there's that sort of complicated little diagram there. It's all about the outside wall. Now, that applies if there is a disconnection point on the roof. If there is a load break switch on the roof, you actually can still run your cables inside the building on the ceiling, because technically they can isolate up on the roof. So there you go. Now, if you've got a cathedral ceiling, well, you're in trouble. So probably you're going to be running your cables externally or have a load break disconnection device on the roof itself. Well, I just checked the time. It's time for me to wrap this up. I try to keep it to an hour, and this has been a bit of a taste of the changes only to 5033 2021, which has come into force in New Zealand. By the way, you've got a 1-year adoption period, so you don't have to use it yet. But if you do choose to use it, you've got to use all of it. You can't pick and choose clauses. So that's come straight from WorkSafe New Zealand. So, yep, it's either all or nothing, new standard or old for the next year. But there are so many advantages in the new standard, particularly with higher voltages. And I haven't got onto it yet, but the fact that you can use the integrated DC isolator in the inverter now, you don't have to have external DC isolators peppering the wall next to your inverter. Those are big pluses. So thanks everyone for watching my return to the Toolbox Tech Talk series, and I'll be back next week. And for those who arrived a little bit late, just a reminder that I do have a course coming up really focused on this issue for New Zealand. It's going to be delivered via Zoom, 2 4-hour sessions over 2 days, and I'll put the link in the chat again for anyone who might have missed it. So that will be recorded as well. So even though it's live and you can interact with me, I do record it and I share it with participants in case they cannot attend the course fully or at all. In fact, I usually have about 30% of registrations don't ever even attend. They just watch the recordings. That's kind of weird, but there you go. So yeah, once again, thanks for watching, and see you same time next week. Okay, check it.